hello to everyone. So let me stand here. Is it good? Yeah. Okay, so today I'm going to tell you about the results I got when working on the CosmoVerse white paper. And basically, I wanted to investigate some stuff so that we can produce nice plots for the paper. So it just happened that it produced actually a paper on their own. And it's related to the statistical particularities of the cosmological inference. So, okay, I don't know if we have seen already this plot, I think yes. But in any case, here the idea of showing this again is not so much to speak about the tension, but to speak about the difference between the data release 1 and data release 2 of DESI. So you can see, you can see this is the DR2 and these are the DR1 results. So we are seeing a great increase in the precision of the results. And the question here is how much of it is due to improvement of methods, of pursuing better systematics, and also how are statistical methods affecting this result. Then here you can see also the supernovae, the different supernovae data sets comparison. So we just heard about this. So this is not new. The question is again, you can see how different the three contours are, where we have Pantheon Plus, Union 3, and DESI 5. And we see significant shift between the mean values and the contours. So again, the question is, we have these results, and we rely on them to study the tension. And the question is how stable they are with regards to effects in the statistical methods. So this is one slide that basically wants to pass the message that we observe some physical objects, which I have written here. So we have these objects, and these objects may have, they have some distribution, but the question is that we may know it or we may just assume it. And the thing is that if they have some specific distribution, for example, if, as we have heard, that there is a difference in the low redshift supernovae with respect to the high redshift supernovae, this is basically a different, a specific distribution that we need to pass to our model. The question is that in most cases we don't pass it, at least for the people who are not doing the experimental part or the observational part, people like me who are using the data for their own models. So this is what I wanted to emphasize here. There are methods to test, maybe I killed it, no? There are methods to test how the data sets compare to each other, like the tension analysis, the suspiciousness, and so on. But here we're not going to focus on this. We're going to focus on the bottom part, which is the one that probably everyone here is familiar with, and it is the data analysis pipeline. So here we have to select a few things before we can get our inference. So we need to select the model. We need to select, of course, the priors, which we know already that are important, because this is the calibration with the early or the late universe. We can also select the likelihood, which is something I'm going to discuss here, and we can select also the sampler. And from all this, we get to the latest part, which is the analysis of the posterior we got. So here I have enlisted a couple of things, because usually we do this part here. This is the parameter constraint and the model comparison. So we have our metrics for model comparison, and we use them to say which model fits the data better or best. But there is also this second part, which is the method validation and the cross dataset consistency and so on, which are additional steps we can do just to be able to be sure about our results and to get more insights into how much is our result robust with respect to statistical effects. Yeah, this is advertising the CosmoVerse white paper because it was the reason for the whole thing. Okay, so first let's start with our test problems. Basically, we have considered, so this is the first part which discusses the stability with respect to the choice of samplers. This is the easier one, obviously, and it's purely numerical. So I need to emphasize here, I'm not questioning the results by the big collaborations. I'm sure they did their best to have the most robust results ever. Here, this is more like a test for everyone else who is using their data for their own purposes. But in any case, I'm not questioning anything of the results that were published. So, okay, we have these three distributions. We have a simple Gaussian, so this is the most often used one. We have the Rosenbrock banana shape. This one is very tricky because you see it's you have a very sharp or narrow region in which we have our values, and the maximum is actually this point here. So for the samplers, this is a very tricky one to sample. And this is the Gaussian mixture model, which basically gives you, if we do the analogy with roots of a system, this system has two roots, so it doesn't have a unique solution. And this can happen in certain models. So these are the three test problems. And then this is basically I took something from the white paper, but it exists also in my separate paper with analysis of all the three distributions and not just of the two. But the idea was that for the white paper we wanted something cleaner because otherwise it becomes very messy. So here we study, this is the runtime versus the dimensions. So on the horizontal axis everywhere we have the dimensions of the problem. And here this is the runtime. I'm not going to discuss the runtime because this is something that depends on the problem and on the data set. So it's not interesting for the current discussion. But I'm going to discuss the accuracy. So here we have tested, on this plot we have just the simple Gaussian and the Rosenbrock accuracy. In the paper you have also the GMM accuracy, which is a disaster, basically. And you can see, now we have two ways to test the accuracy. The first one is just to check the distance from because this is a test distribution, so we know where our maximums are. So it is just to test the distance between of the inferred value from the actual distribution. So this is the simple accuracy. And then we have this Wasserstein distribution accuracy, which is much more involved. But it has the property that it's actually more suitable for distributions. And the idea here is that when you have a higher dimension, which is running in some kind of limited volume, basically you don't have infinite distance between the possible points. So at some point you cannot get very low accuracy in the simple way, simply because your volume is fixed. So this is why we get this more complicated distribution accuracy, just to be sure how precise our methods are. And what we see here is basically that while the simple accuracy is kind of saturating at some point for very high dimensions, for this Wasserstein distribution accuracy actually falls dramatically for anything bigger than 6 in terms of dimension. And we need to remember that this is actually the dimension of the omega k W0WA CDM model. So basically this is not so impossible to get, this situation here. So this is something to keep in mind when you're running your inference. And this is the main conclusion from this slide, and also that basically you get different performance from the different samplers, but again this is not something that should guide your choice. Now, for the BEO studies, what is important is basically that our distribution is not for the dark energy models, it's not Gaussian, it's some kind of curved thing, and this is something that is known, so this is not some kind of new information, it's just I want to emphasize on this, that you have this curved distribution. So this here is not a posterior, this is actually the analytical likelihood that I plotted for the sake of showing that how it's supposed to look. And also you can very easily see this in your posterior, especially if you don't use the cleaned up posterior. that you get from some of the plotting packages, but you just plot the actual points from your chain. You have this stretched object that looks a lot like this. And so this basically is how your posterior is looking like. Now we have this very cluttered, of course, plot. But the idea here is the following. So we have the cosmological models. These are the number of dimensions. So with 1 is lambda CDM, with 2 is omega k CDM. Then we have WA CDM, and then we have omega k WA CDM. So this is the idea. This is the matter density, and here are all the other parameters. The ones with the small errors are actually this is the curvature density, and this is why it's so small. And here you see the deviations from the fiducial values I've chosen, so this is why everything is on the same plot. And what is the moral here? The moral is that different samplers, so here you see we have a lot of samplers. We have nested samplers, we have 2 nested samplers. Actually, we have MC, HMS, and so on, HMC, and so on. So we have lots of samplers. The results are very similar. So basically, the sampler is not the thing that is so important about your cosmological results. What is important to notice, it's not new, but it's good to see it, is that when you add the dark energy models, you automatically get these huge error boxes. So basically, this is again related to the fact that dark energy models don't have the simple Gaussian distribution, and instead they have these curved banana shapes. Okay, so now we move on to the likelihood analysis. So this was the first part, which was dedicated to the samplers. Again, here what the main conclusion for the sampler is, the sampler doesn't matter. What matters is your distribution. And in the case that you expect specific distribution, you need to make sure that your sampler first can handle it, and second to check how it handles it actually. Now, we move on to the likelihood analysis. So this is the well-known full likelihood for the BEO data set, so nothing new here. What we know about it is that it cannot constrain the sum horizon and the Hubble constant separately. They need to be constrained together. So in order to do that, we can calibrate with the early or the late universe, or we can assume some matter content of the early universe. All of this fall in the first box in the big info box I showed you. Okay, the second. So this is choice of priors. So basically, if we choose priors, we know that we get the Hubble tension, and this is nothing new. So the question here is what we can do. One thing we can do is we can, of course, calibrate our results any way we like, and we will get some results. Something else that we can do is we can remove this parameter beta or beta from our likelihood, and this is what this talk is focused on. So on the last conference, I talked a lot about the marginalized likelihood, which we get here. This is basically obtained when we integrate out our parameter beta from the likelihood, and then we use this chi-square to run our cosmological inference. I got a lot of questions back then, how this compared to the profile likelihood and so on. So this is why I wanted to make this paper, just to compare them, to see how they compare in reality. And so here we have also the profile method, in which basically for each iteration, you get your cosmological parameters, and then you minimize your chi-square with respect to your parameter beta. So this is a computationally intensive procedure, because you do it on each step, you get this additional minimalization. So this is the second way to go. And then we have this additional Taylor expansion method, which is an approximation. So in this case, we are assuming a quadratic expansion of our likelihood, and then we use the minimum of the parabola to get the value of beta that optimizes this chi-square. And so this is the third likelihood that we're gonna explore. Okay, no, this is not the correct. Okay, so these are the results which we got for the matter density. So everything here is the omega matter. when we have lambda CDM, omega k CDM, WWA CDM, and omega k WWA CDM to connect with the dimensional analysis that we run in the first paper. And then we compare the different likelihoods. So here with purple, this is the full likelihood with priors on H0 and RD. So basically, this is just for comparison. The reason for this comparison is the following. So the claim was that by marginalizing on our parameter beta, we're going to extend the error boxes. What we're saying here is that the error boxes are not extended. They are pretty much the same. While the prior is not so wide for H0 and RD, it's also not so small. So it's something normal. So here we see that the error boxes are pretty much normal. And what we can see, basically everywhere, is that the four likelihoods give very similar results. The actual difference comes either from the data set that we're using, because here we have BAO plus supernovae, which is Pantheon plus, and BAO plus CMB, which is a Gaussian prior coming from the Planck data. So basically we see that the likelihood gives us pretty much the same result, which is basically showing that we can use the marginalized likelihood if you want to, and we're not going to lose some dramatic precision from it. Also on the plot you can see the ABC simulation, which doesn't assume any likelihood at all. So here the idea was to emphasize once again that just having the likelihood is also adding information to our system. So basically, if you don't have likelihood, you get these huge error boxes, unless you make the priors very informative, because everything here but the BO plus CMB is with flat priors. So unless your priors are very small, you're going to get these huge error boxes. So this is not a solution to our problem. So this is the first thing I wanted to say on this plot. And then, so basically you see how the data set changes your data. But what changes the data the most is actually the model that we're using. So for the smaller models, the lambda CDM and omega k CDM, you get these nice error boxes, and everything looks more or less normal. When you add the dark energy, you get these huge error boxes, and more importantly, your matter density shifts. So at least the mean value. So this is something that is very noticeable from our results, while having the CMB prior basically makes everything very fixed, so there is no much movement here. So this is one thing. We see that we are outside of the CMB mean, which is here, with the gray area for the BO points, but everything else make it closer. And finally, something, okay, I'll say this in the next slide. So this is where we focus on the dynamical dark energy alone. So again, we have the same legends. This is for W0, this is for WA. And what we see is that the BO alone data is definitely not anywhere near lambda CDM. While surprisingly here, when you add the supernovae, you go lower, and the error boxes shrink. This is not exactly the same as the DESI results, but we need to remember that this is basically a different likelihood method, and so maybe this is the reason for this result. And also we see that even with the CMB value, we are barely touching this line. So again, basically we're outside of lambda CDM. This result stays. The WA equals 0 is somewhere here. So we see that the BO data alone is again outside of this region. But I need to emphasize something here. So the point of this paper wasn't to challenge the cosmological results. Actually, the idea is to just test the statistical effects. So this is the important part. So I'm going to move to the other part of this work. And this is basically the study of the posterior distributions. So what we have here we have, so we have run our analysis, we have produced our posteriors, and then we want to analyze these posteriors, the results from the chains, alone, without any more inferences, to check how much the assumption of Gaussianity of our distribution stays. And this is what we see. So these are the two, so basically here there is a line, the yellow line, which distinguish two different reconstructions of the posteriors. So the one is with the effective Gaussian method, this one is with the Fisher method. So there are two different reconstructions, but they give very similar results. So on the top you have lambda CDM and omega K CDM, and here it's omega K CDM. I didn't put also lambda CDM so that it's not so cluttered. And basically we see that for these two models we have very good reconstruction of the Gaussians. On the contrary, when we have dark energy, we see that the reconstructions break down. So you see the four likelihoods that we are testing now are giving very different curves. So this is for WWA-CDM, this is omega K WWA-CDM, and this is just WWA-CDM because with the omega K it becomes even worse. And basically what we see is that in both cases the Gaussianity is breaking down. And this can be also measured with other methods like if you measure the skewness and the kurtosis and so on, which basically shows you how Gaussian is the distribution. And all of them say that the dynamical dark energy definitely cannot be fit with a simple Gaussian the way that we naively want to do. So this is the first result. And then finally, we have the information content of the models. So this is something that is independent from the Fisher reconstruction, because obviously we saw from the previous slide that the Fisher reconstruction is not working very well because our assumption of Gaussianity is not working. But this thing is independent from it. So basically, we think it can be trusted. What we see here. So we see the how much information we get from each data set. So here we have the BO, BO plus CMB data set, and BO plus supernovae. And here are our models. So we have lambda CDM, omega K CDM, and the two extended models. Here is the dynamical dark energy alone. Now, the first thing that we see, and this was, so the first thing I need to mention is that the CMB part makes sense to have higher information content simply because it has a Gaussian prior in order to impose the CMB values. So because of this, it has higher information. Basically, it constrains better the results. But the thing that is interesting here is first that omega K CDM has very high information content for all kind of data sets, which is very interesting actually. Basically, our data sets are very sensitive to this model for some reason. So this is the first thing. And the second important thing that can be noticed is that basically the BAO plus supernovae constraint for the dark energy model is also with very high information content. What you can see is basically that this is much higher than the lambda CDM model and also much higher than the BO data alone. And this can be seen also from here. So you see that in this plot, we have much smaller error boxes here than here. So basically, our method, for some reason, is very sensitive to the dynamical dark energy when we add the supernovae data, while without it, it's not so sensitive. So this is the result from here, and basically this is my conclusion. So the first part, the first thing to take away from this talk is that if you're doing any cosmological inference, if your model is for some reason predicting some kind of transition, you need to remember that this cannot be approximated with a simple Gaussian. It needs to take into account the actual theoretical distribution of your model. So if your model is predicting, is needing the Gaussian mixture model, then first you need to make sure your sampler can fit it, and second you need to make sure that the precision, that your number of dimension is not in the area where the precision is really bad. So, or if it's in that area, you have a lot of parameters and you need to fit that, then you need to just increase the precision of your method in any way you can. Otherwise, all samplers are made equal. It doesn't matter what you choose. And also to remember that the shape is a banana, which is the important part here. And then you have this part about the likelihoods. So basically, the choice of likelihood is not so important. You can, the marginalized likelihood or all the other likelihoods give you good enough results if you cannot do, for some reason, the full likelihood method. So you can use them if you need them. Then the important parts for our purpose today about talking about the tensions are here. The dynamical dark energy model shows this non-Gaussian structure, so it needs to be taken into account. The information that the data sets have is not the same for all parameters in all models, so this also needs to be taken into account. Something that came out from the Fisher matrix analysis in this line here, which says that there are directions in the parameter space that are not constrained at all for the dynamical dark energy models. So this is important when discussing tensions and saying how different our results are from one CDM. Some directions are simply not tested, or they are tested, but they're not constrained. So the tension between the data sets is known, so this is not new. But basically, what the conclusion is that sometimes the methodological choices we make may be as big as the tension we want to study. So basically, we need to pay attention to the details because they are important, especially when we want to go to smaller and smaller systematics in order to prove the tension. So this is it. Thank you for your attention.
Thank you so much for your very nice talk. I'm wondering, since we published with several collaborators in 2023 and 24, the analysis of non-Gaussianity for the residual of supernovae 1A, BAO, and quasars, did you check also the logistic and the T-student distribution for the BAO data?
No, so I didn't. Basically, I checked what I have here because it turns out that just adding the supernovae is very hard for my laptop. So this is what I did.
Thanks.
Thank you very much. After all this work, what sampler do you suggest for cosmological studies? For example, I have a new F of R or whatever modified gravity model. What you will think that would be the best sampler to use?
I don't know. I mean, literally from this plot, you can say that the sampler doesn't matter almost at all. Basically, what I used in this case is, so for the likelihood analysis, I used Polychord and MC. So these are the two that I checked. But basically, from what you can see here, everything works well, except for the maybe the traditional method. This is not working so well, but everything here, like HMC, works very nice. Actually, I like the Hamiltonian Monte Carlo, but it's a bit tricky to implement. But MC is working very nice, I think, and Polychord also.
Just while we're talking about samplers, have you thought about looking into Nautilus, the machine learning emulator optimized sampler? Runs lightning quick. I'd love to see how it performs here. It's called Nautilus.
No. Right. So these are the samplers I used, which are not little, actually. But is it nested or not?
Yeah, it's a machine learning optimized nested sampler.
No, I haven't used it, but I can try
it. If you could add it to your plot, it would be really cool because like I said, it's lightning quick.